Here you can see a picture of the machine. And we know that there are mainly two big technologies for optical biometry. The traditional one, PCI, partial coherence interferometry, is the one that was available on the original IO master and is still used by several devices like the Pentacam AXL, the Galilei, and the Nidec, other old generation instruments. This technology has some advantages. It's relatively cheap, is simple, it's based on the Michelson interferometer, which has some problems. It can suffer from motion artifacts if the patient moves. And as we all know, it is difficult to measure the axial length in eyes with subcapsular cataracts or very dense cataracts. And on the other side, we have the swept source OCT biometers. And here you see the most recent, the last generation instruments, even if they are already 10 years old, some of them, or even more than 10. It allows us to take simultaneous images of all the interfaces, and you can see not a simple A scan like with PCA on the left, but you see all the interfaces from the cornea to the iris, the crystalline lens, and finally the fovea. And it does not suffer as much as PCI from motion artifacts because you have simultaneous scans of the whole eye. The problem is that this is an expensive technology and is quite complex. So the approach of CSO has been different. It is not the only manufacturer, but is one of the few basing optical biometry not on swept source but on spectral domain OCT, so with a different wavelength of 840 nanometers rather than the usual 1050 nanometers used, for example, by the IO Master or the iStar. It's a relatively simple and cheap solution which enables us to take a simultaneous scan of the cornea of the anterior segment and the posterior segment, showing the interfaces. So here you see that you can get the scans of the anterior and posterior segment, and this eliminates problems with artifacts coming from movements of the eye. These are the technical features. You can measure axial length from 14 to 36 millimeters with a 10 microns axial length resolution, a lens thickness range from 1 to 6 millimeters, and a resolution of 10 microns. It takes, when you take everything, all measurements, it takes about 5 seconds to measure axial length, ACD, and lens thickness. Of course, a lot of work has been done to speed up this time, to shorten this time, because especially with older patients, having shorter time for acquisition allows us to get better measurements. Just a few seconds acquiring, and once acquisition is started, completed. So it took about 5 seconds to take the whole acquisition. And this is the printout that you get at the end, where you can see from the cornea to the fovea. And you see, now you cannot read probably the numbers. Anyway, on the right, there's the same patients measured with the IO Master 700, and the numbers more or less in this specific case are the same. And you get all you want from axial length to ACD, aqueous depth, which is the distance from the endothelium to the crystalline lens, lens thickness, CCT, and all the keratometry values. And we did a preliminary study I presented very similar case numbers 1 year ago in Florence, but these are totally different patients with a totally different software. And when you look at these 58 eyes, where we took one measurement with the MS-39 AL and the IOL master, the only statistically significant difference was for ACD. There are minor differences for K flat, for K steep, for K average, and probably these differences may get statistically significant with a larger sample size, but you see that these are not clinically significant. And the difference for ACD is not surprising because we all know that there is a bias on the IOL Master 700 that is due to the original IOL Master. In order to maintain the same ULIP constants when the IOL Master 700 was released in 2014, DICE had to make some adjustments on the anterior chamber depth because the original IOL Master measured the ACD through a lateral slit, not coaxially. And this made the measurements of the original IOL Master for ACD shorter than all other competitors. And this was we know that the anterior chamber depth is important for some formulas like the Huygens. If the new measurements from swept source OCT would not have been adjusted by ZEISS, probably some constants on the ULIP website would have not be valid anymore. So the IOL Master provides us with slightly different anterior chamber depth measurements compared to all the other optical biometers. Anyway, the difference is just 0.1 millimeter. And we did the Bland-Altman plots for all values just to tell you that they are extremely good, and agreement is especially excellent for axial length. You see that the 95% limits of agreement is just from minus 0.08 to plus 0.03 millimeters. So the IOL Master and the MS-39 AL measure the same axial length, and I think this is a very good result, but they are also good for the other values. We, in this preliminary sample, we did not assess the repeatability of all the other measurements taken by the MS-39. We already published them in 2018 when the machine was made available, and they were excellent. I'm just reporting the repeatability for the new values, the anterior chamber depth as measured by optical biometry, lens thickness, and axial length. And you can go directly to the last row, the coefficient of variation, and you see that is really low. It's around 1.4 and 1.2% for axial, for ACD and lens thickness, and just 0.05% for axial length. This based on 3 consecutive measurements taken with the new MS-39. And IOL power formulas are not yet available. You have ray tracing, of course, but these are the formulas that should be available. So this is a new philosophy, I think a very smart one. These are the formulas that are available on the ECRS website. There are a lot of papers all over the world showing that new formulas are more accurate than the Holiday one, Hoffer Q, SRKT, and also compared to the Huygens. So there's no sense to go on providing us with the PDF, with printouts, with the old formulas, even if somebody is still used to rely on the SRKT. So I think that it is the right direction to use the Barrett, the Kane, the Evo 2. The Evo, and the Hoffer QST. Why? Here you see, for example, this is the slide that I think made the Barrett formula famous back in 2016. This was shown by Jack Kane, the author of the Kane formula, and you see that the blue line on the bottom is the Barrett formula, and on the y-axis you have the mean absolute error, which is the absolute error, the absolute value of the prediction error. What is the prediction error? The difference between the post-operative refraction and not the target, but the predicted refraction. Of course, if I operate two patients, and one adds up -5 and the other one ends up +5, and I take the arithmetic error is 0, I feel very happy. The patients are not very happy. So that's why we always consider the absolute prediction error, which would be 5. And here you see on the left, in the red column, the short eyes, shorter than 22. And you see that more or less all formulas are bad. But when you go to the gradually to the right and you see the medium long, long eyes, you see that the Barrett, compared to the old generation formulas, is much better. After Kane showed this slide, it was at ASCS and then published on JCRS. I think that everybody all over the world started using the Barrett formula that had been available for 10, 15 years, and nobody was looking at the Barrett formula. But after this paper, everybody, including myself, started using the Barrett. And here, this is one of the most important papers that have been published and that justify the use of new formulas where, again, okay, it's difficult probably to show, but here you see, okay, the percentage of eyes within with a prediction error within half a diopter is 80%, and number one is Barrett. So another independent paper showing that the Barrett was the best. Then there was an update showing that the Kane was the best, followed by Olsen, Barrett, Evo, Hill RBF. So, and the old formulas are still good, but not as good as this one. And we also published, when we published the Hofer QST, we had the same results, that new formulas are better than the old ones. And this was the first talk about the MS-39 AL. Then I would like to provide you with the updated results for IOL power calculation with the ray tracing software by CSO in post-myopic LASIK.